In AC, you're going to have 40 volts and negative 40 volts. So in finding your DC voltage, you need to find your peak to peak as part of your formulas. So you can find your voltage secondary peak voltage. Now, to find your voltage secondary peak, we found our voltage secondary. So let's say we stepped it down from 120 volts to 40 volts.
Right.
But there's a peak to peak voltage within a sine wave.
Right.
So what we have to do is find our peak voltage secondary peak to peak. So if we're doing that, it would be our voltage secondary times the number of waveforms, 2, okay? But if you look, the 40 volts isn't there all the time. There's 40 volts here, there's 20 here, there's 20 here, there's negative 20, negative 20, 35. It's not always at 40 volts. So we have to look at it. If we were comparing all this as 2 full waveforms, we have some missing voltage right here. Okay? And we have to account for this missing voltage. So instead of saying 1, 2 full waveforms, we have to account for this missing voltage because it's not at 40 volts or negative 40 volts the whole time. So instead of multiplying times 2, the math's been done and they took out in a sine waveform the missing voltage, and it's not multiplied times 2, it's multiplied times 1.414. So we take out, I think it's like 5 or 0.586 is what's missing in this 2 full waveforms, because there's not 2 full, it's not all the time at 40 volts, because as you're going up and as you're coming back down, you're missing voltage. Like right here, this is 20 volts. So we can't say 40 times 2 because it's not there.
Right.
So to account for this missing voltage, they've done the math for us, and this is a set multiplier. We multiply our voltage secondary times 1.1414 because we're not always at 40 volts or negative 40 volts.
Okay.
Does that make sense?
It does. Now the other thing I wanted to ask you about is when you calculate your VDC. Okay, when you calculate your VDC, what is that formula again?
It's
the
it's our voltage out times either our half wave or our full wave.
Okay, so in our half wave, it's 0.318.
Right, and that's just the multiplier.
Which seems like that is somehow in relation to if you have peak and you want RMS, you multiply it times 0.707.
Right.
The thing that comes to my mind is, man, we're not getting very much voltage out for the amount of voltage we're putting in.
Right.
You think that is in relation to the number left over after you would subtract? If you had 1 or 100 and you subtracted 70%, you'd have 30% left over.
Yeah.
Is that where they're coming up with that, or you don't know?
I actually looked at it one time, and I was going to work it out, and it's a long thing. It has to do also with the sine wave and the way the pulses do compared to, and also minusing your voltage drop of your diode. I mean, it does a bunch of stuff. I can't remember exactly where they get this figure.
Yeah.
It has to do with the conversion of the two. But it is something like that. It has to do with the RMS voltage converting it to DC voltage, and you're missing your frequency and your triggering changes or something like that. I can't remember. What I tell them is when you get to DC, to convert AC to DC, there's 2 multipliers. There's a half wave multiplier and there's a full wave multiplier.
Oh, okay. That's good.
Yeah, there's just a multiplier, and these are set. So whenever you're looking for a half wave, we multiply times this. If we're looking for a full wave, we double it because we're taking advantage of both sides of the waveform. If we're not, we're only taking advantage of one side of the waveform.
And the only time you take your to get your VS or VS peak, I can't remember, but the only time you divide it by 2
is if
it's center tapped. You don't
what
do it on the
happens
full wave bridge.
Right, and because we're center tapping the transformer on the on the full wave, because if you don't, what ends up happening is you have plus, minus, you don't have nowhere to go, because from positive to negative, current doesn't flow. So you couldn't go, it wouldn't work. So what we do is we center tap it, we come down here, we come around, and this center tap is actually our negative terminal to our positives. So what happened is you go negative, come around, go all the way through, then go negative to positive, then back to positive. Then on the downswing, you go negative, come all the way through, and it comes back negative to positive to this terminal. So it allows you to flow from negative to positive.
I see.
Yeah.
Okay.
And this can also be drawn like this. So this half wave can be drawn like this. So whenever you're looking for your current of your diode, you have to split it because it's in parallel. So whenever you're looking for your diode current, half of it's going this way and half of it's going that way, because you have the same voltage, you have the same everything, because these are both the same kind of diodes. So whenever you're doing your current of your diode, it's your load current divided by the number of legs in parallel you have of diodes.
I
So
see.
here's two. Now when you get to your bridge rectifier, it can actually be drawn like this also, but now you have two in series. You still have just a split,
Right.
so your diode is still the same, but you now have two diodes in series.
Yeah.
So your 0.7 and your 0.7 end up being, because in series, voltage adds up. So 1.4 is going to be your VB. And 1.4 on this side. You don't add these up because in parallel, voltage stays the same. 1.4, in series, they add up. So you add these two up, 1.4 is now your voltage barrier.
I got you.
On the other two, they're 0.7. On the bridge, it's 1.4.
Right.
And it's just because series and parallel.
Okay.
Does that make sense?
That helps me.
Okay,
Yeah.
sure. Good.
And so you don't get